In this presentation, we will discuss how to monitor your heart rate using the camera available on your mobile phone. The implementation is based on Matlab, and we will go through some of the signal processing steps required to make the monitoring in real time. We will take a video using the camera while blocking the view with your finger. The idea is that the amount of blood reaching your finger will change depending on your heartbeat, and the intensity of the pixel values in the image being captured will change accordingly. The intensity of the pixels will change also if the amount of light coming from below the finger changes, as well as changes on the pressure or position of your fingertip will also affect these measurements. Then we will need to do some processing of this signal. Here is an example of an image or video frame. The amount of blood is measured by averaging the pixel values of each frame. On the right, you can see how a one-dimensional signal is formed this way. I will be calling this signal x of n. Notice also on how difficult it is to discern the changes on intensity on the video, but they're definitely there. Also notice how it is difficult to see some oscillatory fluctuations of x of n depending on your heart rate. For a real-time implementation, I need to consider the amount of time that is required to capture each video frame into the device that will be doing the processing. Once I have a frame within my computer device, I need to consider then the data capturing time. And also, once I wrote a program to process this frame, that program will require some time to be executed. So I have to also consider the program execution time. So these two times together should be slower than the time it's going to take me to acquire the next frame in the video. So that time is just given by 1 over the frame rate. Heart rate ranges from 40 to 230 beats per minute. And in order for me to convert these quantities into hertz, I just need to divide by 60. So that's the frequency content of my original signal x of n that I should focus on in order for me to estimate a heart rate in a reliable way. Now, a sensible frame rate to use will be 15 frames per second that is given by the maximum frequency 3.833. Nyquist tells me that I should sample twice as fast at least, so 15 frames per second is a good amount. Now I'm going to use a video reader object in Matlab with that command. This is just the file name where the video is stored, and I'm going to enter into a for loop in which I'm going to start a timer at the beginning, and I'm going to read 2 frames. The reason for that is because the original video is recorded at 30 frames per second, so this will reduce it to 15 frames per second. That is an example of a frame, and what I need to do is to convert this frame into a gray level value image, which is given by this command, RGB to gray in Matlab, and then I just take the average value of that, and I'm going to store it into a variable that I'm going to call x. Then I'm going to stop my timer and save that information into this other variable. And that's just the end of my for loop. And I'm going to take the average value of this vector here, and that's the result. It is 0.016 seconds. And that value is less than 1 over 15. So far at this point, my data capturing time is fast enough. In general, an expression of a filter can look like that. So it consists of m zeros and n poles. And those subtractions z minus z1, z minus z2 of two complex values define a vector. So for example, if I have a 0 at that position with that particular value in the real and imaginary axis, it's going to be subtracted by a particular value in z, which once again can be complex, so it will be another vector. So the subtraction of those two vectors yield this one, which once again is the subtraction of those two. Now, I can rewrite these complex values in polar form where they will have a magnitude and a phase as it is indicated there. And this will allow me to see that in the Z transform as expressed in that summation there, if I compare it with the discrete time Fourier transform, which is given by that, I can see that the only difference between those two expressions is if we allow Z equals to e to the j omega, they actually become identical. So that's the relationship between the discrete time Fourier transform and the Z transform. So that would restrict the values of Z. They're no longer in the Z domain, be placed everywhere in the real and imaginary plane. But if I restrict those subtractions by Z lying in e to the j omega, that would give me an indication of the frequency response of this system. And this Z equals to e to the j omega will restrict all these values along the unit circle, as this is a vector and a phasor with amplitude 1. And as omega changes, it will describe that circle. So let me put this in a smaller font, and let me give you an example of the real and imaginary plane. And the circle that you see there, it's the unit circle. And I will be evaluating Z values along that unit circle. So Z is equal to e to the j omega. At that particular frequency, it looks like 45 degrees or pi over 4. That's where it lands. So every time I have a 0, this distance here are 1 of that 0 is just the distance between that 0 to e to the j omega at that particular frequency. So it has a magnitude and a phase, and that will be the term here of a system that consists of only that 0. I can add another 0 also in the real axis, why not? And once again, that vector defined between the differences of Z2 and that point at that specific frequency will have another magnitude and another phase. So that will be the green part. I can add poles, so that one will have that specific distance to that point in the Z and values that I can evaluate along that unit circle at that particular frequency, and it will have that phase too. Most likely than not, if this is a system that is going to have an input with real values, and I would like to obtain an output with real values, my system will require the complex conjugated version of that pole, which is right that one, which once again will have a magnitude and a phase or an angle with respect to that frequency that I'm inquiring. And that will be that pole there in the expression in the middle. So now, if I need to design a bandpass filter, I would like that bandpass filter to be right there, those frequencies between 0.6 and 3.8, and the center frequency, if you do the numbers, will be 2.25 hertz. Now, if I would like to design this filter by placing poles and zeros, I can do that by placing a pole right there, and I will name it P1, and I will be evaluating the distance between that pole and values in the unit circle. That's the angle of the pole at various specific frequencies. So e to the j omega will be traveling along that circle. And for example, if I choose 2.2501 hertz as the frequency there, I can realize that at that particular frequency, that distance d1 from the pole to the unit circle at that particular frequency will be the smallest. So that's the expression of h of z, and the magnitude will be just 1 over d1. And once again, d1 at that particular frequency is the smallest. So it will peak there, and it results that that frequency is the center frequency in my bandpass filter, and that's something I need. I will need its complex conjugated version, which is that one, and my final system with these two poles will look like that, with its magnitude being equals to 1 over d1 and d2, where d1, once again, is the distance between pole 1 to that particular frequency, and d2 will be the other distance. So if I do this, design my filter with these two poles, that's the expression that I have, and those are p-values this one, and this one, they are the same, it's the same distance of the pole to the unit circle. So that's the other one there. And that distance is given by that RP. No? Okay. So now, if I would like to calculate the coefficients on the difference expression, on the difference equation, I will use the command poly in Matlab, where in this command I just need to give it the roots of the polynomial, and by doing this command, it will lead me to the coefficients of the second order difference expression. So if I run it and plug it in into the expression of h of z, it gives me these coefficients, 1 minus 1.11667 and 0.9025. I can then just multiply y of z times this polynomial, x of z just multiplies times 1, take the inverse z transform of that expression, and I ended up with this very simple difference equation. Notice that my output of the filter only requires the current input of that signal and this product of the previous values that I obtained in n-1 in n-2. So that's extremely fast. Now let's see how this filter looks in frequency. So I'm going to use, once again, Matlab. To do that, I'm going to use the command flexset, and that command requires me to give the coefficients associated with the input, that's just that one, the coefficients associated with the output, which I computed before. I'm going to tell Matlab to compute 1,000 values, 15 corresponds to the sampling frequency, and I'm just doing the plotting there. And this is how it looks. That's the frequency response of this system with two poles, and it's doing what I wanted to do. It peaks at 2.25 right there, and as you can see, even though it's a resonator, it resembles a bandpass filter. If I want to improve my filter, I can add 0 at that position, and what that 0 is going to do is going to take care of this strong peak here, the one at 0 frequency. So notice that that 0 place there will add this part here in my expression of h of z, and that r1 is the distance, once again, between that 0 and that black point in the unit circle at different frequencies. So that is r1. Now, the interesting thing here is that as I approach the 0 frequency, that distance r1 becomes smaller to the point that where I'm almost at the top, that distance will become eventually 0, completely blocking the 0 frequency here, which is something that I want. So going back to that position, if I add a second 0 there, what is going to happen is the following. I'm going to add in the expression this term, as you can see there. Now my difference equation that identifies the filter that I want looks like that, second order, and as I move towards higher frequencies, as you can see there will be a point here when I'm approaching the highest frequency of 15 Hertz, where that little distance here corresponds to this distance in the expression, and it will lead to 0 at the very highest frequency, which is some frequencies that I'm not interested. I just was interested in passing this part. So it's just a minor change that would translate into these following coefficients for that part of the difference equation. So I'm going to use the same command poly. I have two roots located at 1 and -1. And the coefficients are just 1, 0, and 1. And that's the type of expression that I obtained by modifying my filter in such a way. So notice that I'm not adding any multiplications. The multiplications here are 1 and 1, and I'm just adding one subtraction. So for almost no computational cost, I will have the following um, filter. Uh, so this is how I will design it. So I no longer have false only, I have zeros, and I will use the command in Matlab to plot the frequency response, and this is the type of result that I have. Notice that in fact we eliminated the zero frequency, we completely attenuated the 7.5, attenuated even more the higher frequencies that I'm not interested, and the cost, once again, of doing this improvement is very minimal in terms of computational time. Going back to the program, I'm going to start the same way I started explaining the timing for the data acquisition part. I'm going to create that video object by using the command in MATLAB video reader that will allow me to extract information like the number of frames and the frame rate, for example, and read each frames and like the one I'm showing you there and display them to if I want to. So I'm going to enter that for loop, which is very similar to the one we explained before. I'm going to be concerned about the time that I'm going to require to read the frames and process them. I'm going to read 2 frames as before to reduce the sampling rate from 30 frames per second to 15 frames per second. I'm going to show each of the frames as an image. I'm also going to compute the average value of the pixels in that frame, and I'm going to store them in a variable x. I'm going to also plot that variable x, as you can see in those commands in MATLAB. And as we have seen it before, that's the average values of all the frames available, which is a little bit more than 160. So that's my signal x of n. In order to do the processing, I know that my filter requires those 2 samples, so I will have to wait a little bit before I process an output because I need the current input as indicated here, x of n, and I need to discard the following input and then wait for the next one and do that subtraction. So I need that. So I will need to wait for those 3 samples in order for me to calculate a current output, which is indicated like that. No? So my current output will need those 2, and I will also need to store in memory the previous outputs that I have at the beginning. So at the very, very first time, I will have to assume that these values are 0. And once again, I will have to wait for 3 frames to start processing that signal and filter it with that bandpass filter, which coefficients you can see here. So I need to design the filter as before, and of course, this part of the program will be outside the for loop. I don't need to calculate and design the filter every time I enter the loop. So I don't need it there. And in this part of the program, I'm just waiting for those 3 samples here. That's the I here, the counter is I, so I'm just waiting for that before I start doing my filtering of the current output, depending on the previous 2. And notice that these vectors correspond to the coefficients of the difference expression and xi minus 2. So that's all the filtering, and I will do it all along that line, or that signal x. So I will be obtaining filtered data like that. So notice how I can see those oscillations corresponding to the heart rate, and now I need to decide how to calculate the beats per second. In order for me to do that, I need to see the frequency of these oscillations, and one way to do it is to use the Fourier transform. So now I have to decide for a length of the Fourier transform, so maybe around 30 or something like that, which is highlighted in the yellow part as here. And after that weight of 30 or something number of frames, now I can compute the Fourier transform of that, check where the position of the peak is, so that I can estimate the bits per second. So I will decide that the length of the Fourier transform and also the number of frames that I'm going to use for computing that oscillation calculation. It's going to be 32, so I have to do that wait until those arrive, and I'm going to compute the Fourier transform of that block, of that segment. I'm going to plot it, as you can see there, and the information that I'm looking for is the location of the peak. So as you can see here, the peak occurs at position 5. This is a frequency index, so the position 5 indicates the frequency there that I need to estimate. Of course, I need to normalize it, so I normalize it by dividing by the length of the FFT, which is n, and I multiply times the sampling frequency, and that would tell me that within that block, the yellow block, my bits per second will be 2.3438, which lies in the range that I was expecting. So that will be happening with these operations. The maximum of the spectrum that I calculated of this block here, I obtain the position and the value. I just need the position, multiply the position times the sampling frequency, which is 15, and divide by the length of the FFT. Notice that if I took 32 samples and calculate the FFT size is 32, and I'm just plotting the positive values here, as you can see there. So I'm going to run the program, so you can see it running. It's running in real time, and it's calculating the bits per second, as you can see there. Now, I'm using a fairly slow computer, a laptop, with specifications for the processor, as you can see there, an i7 Intel, 2.6 gigahertz. That's the speed of the processor, and nevertheless, it's not like a top-notch computer system. The elapsed time is 0.0315 per frame. And remember, we need it to be less than 0.0667, so it's able